Okay, so let's get started. So welcome back. This is the last lecture of the course. So today's lecture is going to be very lightweight and very high level, like general view on reinforcement learning and like what are the next things that you could study after this course and so on. But before we begin, like a couple of quick administrative things. Like so, A3 is almost graded, so we will be releasing the grades today, hopefully tonight, let's say. And we have been very, very lenient with A3, like because of all the issues with active. Okay, so normally you should be happy seeing the marks, but we will still have like next 5-day period of regrading, like if you have any concerns about the grades. Okay, but after that, like all the assignments are done. And about the project, I know that I should have released the schedule for the presentations. Like I haven't. Like I'm going to do it today, but I already gave you the dates. Like so it's going to be the 2 days after the exam. Like, but for people who want to travel immediately, it's going to be on the day of the exam evening. Like so, there's going to be a lot of slots. Like so, it's going to be more easy for you to find a 10-minute that works for you. Okay, so. Other than that, finally about the exam. So there were a lot of questions about the exam last week, but I forgot to like take those questions back towards the end of the course. Do you have more questions about the exam? Like so there was a question about like how to prepare, but I think I kind of talked about it last week. So unfortunately, there is no previous year questions. Okay, so this is the first edition of the course. Like so maybe next year we will have this year's exam paper. So that is always a challenge, like when it is the first edition. Like so I can point you to some papers from like other universities, like but then maybe they're going to be a different difficulty level, right? Like so I don't want you to assume that, for example, the questions are going to be in the same difficulty level as like previous year questions that you can publicly find online for other courses. But if you are curious to see other universities like reinforcement learning like final exams, like so I think some of the final exams of McGill's oral course is publicly available, like so is Stanford's oral course. Like so there are a lot of oral courses like whose final exams are publicly available. Okay, the only reason why I'm not giving them as representative is like that's not how the exam is going to be. So so given that this is the first edition, like, and given that a lot of you felt that the course is heavy, like, so I'm working on reducing the load for the next year. Okay, but to balance all of those, like, we will have an easy exam. Okay, so probably I should not say that now. You're going to be more like lethargic about preparation. Like, you should do your best in the preparation, like, but like exam will not be very difficult. Okay, so if you ask me how to prepare, the only answer that I have, like from the beginning, is just the lectures. Like I don't expect you to read the book, even though it's like you must read the oral book. Like it's one of the great like textbooks ever written. But I don't expect you to read books. I don't expect you to read extra papers. I expect you to know everything that has been taught in the class. So I will set the questions only based on what I have taught in the class. Okay, so if you are a student who attended the classes regularly and like refreshed your memory once in a while, like, so you should find the exam easy. But if you skipped all the classes, well, this is for people who are watching the recording later and was only watching recordings of lectures corresponding to the assignments, it's going to be a problem. Okay, like so, like if you are a regular in the class, like so you should find the questions answerable. Like the exam will be purely based on like whatever I have taught in the class. You had a question?
Are there self-assessment questions?
We don't have self-assessment questions here. Like, so I will try to do that for the next year for sure. So, like for the ML, like I prepared the self-assessment questions like in the past. So I'm giving those self-assessment questions. Like, but for all we don't have it yet. So I will. It will be there for your juniors. Like, but for this year, we don't have self-assessment questions, but there is a question in the chat, like, so will the exam structure be similar? Similar to what? So, well, I don't know what, okay, will the exam structure be similar to other university courses? Like, yes, of course, the structure is going to be similar. Like so given that this is only a 2-hour exam, like probably you are going to get 5 to 6 or 5 or 6 or 7 questions to answer in 2 hours. Like, and it is useful to see other universities' exam papers, of course. Like, so, like you might get an idea of like what kind of questions people ask, and you should also be able to answer those questions, like with whatever you have learned so far. Any other questions? One thing that okay, so there is a question about students with extra time. So yeah, I think students who have the SESH approval, like for extra time, you can submit in the same grade scope link. There's not going to be a second grade scope link, but you will have, I don't want to say wrong information now, but I think you will have extra 1 hour. Okay, one thing I want to clarify, like for students who need extra time, exam is for 2 hours, okay, not 3 hours. Like, so you will not get 4.5 hours extra, like you will not get 1.5 hours extra. So like you will only get 1 hour extra. Like, so like if your exam is for 2 hours, like it's going to be 3 hours plus the extra hour for like submitting and tagging in grade scope. Okay, so the exam is at 1:30, right? Like, so everyone should submit their answer sheet by 4:30. Yeah, and ACSH students will get an extra hour, so by 4:30, sorry, 5:30. Okay, so I think I kind of mentioned this before itself, like, but I want to highlight it again. So exam paper is going to be set for 2 hours, not 3 hours. Like some students ask me, is it going to be a very long exam? I don't know if it was from the ML course or oral course. Like, so exam paper will be set for 2 hours. However, you can use the entire 3 hours to write and upload if you want. Okay, you don't need to stop exactly at 2 hours and submit in 2 hours 5 minutes. Some students did that last year. So, and there might be some other students who are still writing. So you have the entire 3 hours, but you should decide when to stop and upload. Like, I will not accept any request saying, oh, I was writing till 4:25 when I was trying to submit, the link closed. Okay, that is your mistake. Like, so you should ideally submit in 2 hours. If you want to take a little bit extra time, take your time. Like, but make sure you submit in 3 hours. Like, so we will not accept any email submissions, and we will not accept any late submissions in grade scope. Okay, so like grade scope is going to be a little bit open, like for people like who are submitting 1 hour late. But if you submit 1 minute late, you get a 0. So like make sure you submit before. And there were also a couple of requests to make it a 24-hour exam. I think it is, well, I can definitely not change it now. So it's going to be only 2-hour exam. One of the, even though I like one-day take home better, like one of the big problem with one-day take home is it is going to clash with other exams. Like, so like if you have, already there are people who have clash, like, so somebody having this exam in the afternoon and another exam in the morning. Like, so it's just going to make the life harder for some students in the class. Like if the exam is 24 hours, like some of you might do only 1 or 2 courses, but there are students who are doing 3 to 5 courses in the semester. So let's just stick to the exam time. Like we will not extend the exam time. Okay, so, and one last reminder. So I have received very few feedback, the official course feedback. So like which you should submit in Moodle. Like, so if you have not done so, like please do it this week. I think it closes by next week. And as I mentioned before, it is very, very important for me that like all of you give your feedback. Okay, so let's get started. So I want to talk about like several. Yeah.
One last question about the exam. So we saw a couple of proofs in the class. So will we be tested on those things, or is it going to be like?
Oh.
Kind of
Okay. Well, the secret is I haven't set up the exam yet, so I cannot give a definite answer. If I give a definite answer, then I should follow it. Okay. Well, I will not expect you to do a proof in the exam time, but you might need to know all those things that we have seen to answer some of the questions. Okay, so I think that's a reasonable answer. Yeah.
Like, do we need to type the answer in latex or like?
That is your wish. Like, so you can
Do formulas or something to type in while during the exam?
Well, if you want to type in LaTeX, you can type in LaTeX by yourself. Okay, so but it is not required. You can either write and scan, but please make sure that your handwriting is legible and your scanning is good. I recommend you to try scanning with your phone or iPad, like if you want to test before the exam, like you might have surprises during the exam. And some of you, I think, just like how I write in my iPad, I think some of you write in your iPad. Like I have seen you doing that even in the class. Like, so you can also write it in your iPad and submit the PDF. Or some people, I think in the past, a lot of students actually typed in LaTeX. Like I can't type in LaTeX in 2 hours. You need to be really fast, like in typing to do that. Like, so if you're comfortable doing that, you can do it. So, but it is not required. Okay. Okay, so let's get started if there are no more questions. No more questions in the chat. Okay. So today I want to talk about some of the general and challenging problems in reinforcement learning, like so which we did not talk in the course, talk much in the course, like so for the obvious reason that this is an introductory course, right? Like so, there are a lot of interesting and significant progress that is happening in reinforcement learning in the last 10 years. Okay, so probably the closest that we have been to those advances was DQN and A3C, which are from 2012 and 2013. Okay, so there is 10 more years of research after DQN, so which is the whole field of deep reinforcement learning, which is a combination of deep learning and reinforcement learning, which made application of reinforcement learning to several practical problems possible. Okay, so we're not going to talk about, we did not talk much about any of these recent advances, but today let's try to cover some of the general next set of topics that you could focus on, if you're interested in reinforcement learning. Okay, but before we do that, we're going to do one summary of the course. So this is probably a useful refresher for you, for your exams. So I will also ask some questions during this summary. You can test yourself. You can test how much you have prepared. Okay, so okay, so going back to the beginning, right? What is reinforcement learning? So reinforcement learning, for people who have already done supervised learning in other courses, is a totally different learning paradigm, right? So reinforcement learning is all about learning through interaction. Which is kind of almost missing or totally missing in supervised learning. In supervised learning, we always start with a data set and we train a model using the data set. So this is completely batch setting, right? And once you have the best model, then you deploy the model. Now, there is a mismatch between the training and deployment phase, because during training, the model had no interactions, right? So, but when you deploy the system, then it is going to get queries from the user. And now this queries that you're getting from the user, they are not IID, right? Like, so like the problem, like the biggest problem with having a fixed data set based learning is like we often make the IID assumption, like which just means that the data set is independent and identically distributed. So for example, like if you want to like do image classification, right? Okay, so or let's take question answering. Okay, so let's say we want to train a question answering system for Siri. Okay, now when you train the system, like you have this huge data set of millions of questions and answers, like so you train the system well and you deploy it. Now, once you deploy, the system is not going to get the same set of topics. Sometimes it doesn't matter what the average performance in the data set was, right? Like so, like for example, when it is close to Christmas, there's going to be a lot of Christmas related queries. Like so, when it is a weekend, there's going to be a lot of silly questions from the kids at home, right? Like so, now this is not IID, like so there is going to be some seasonal shifts, like so some like regular patterns and like some temporal like differences that is happening in the deployment phase, right? Like so now this is kind of not handled, which often leads to issues with using machine learning, like and also learning after deployment. Okay, so typically when you use machine learning, like so you learn the model and you just deploy the model for inference. In some sense, after deployment, the code is just a glorified software piece, right? Like so it is a program which takes an input and produces some output. There is no learning happening, right? Like so on the other hand, like if you can learn while interacting, like so learn with the feedback, so you have a system that can continuously learn and just keep getting better and better. Okay, so we are going to talk about such continually learning systems soon, but let's come back to oral now. Like so, like to contrast with the supervised learning setup, like in the case of reinforcement learning, like entire learning happens through interaction, right? Like so, you have the agent which interacts with the world, right? Like so, at every time step, agent sees some state, okay, and it takes some action based on the state. So once it takes that action, it is going to receive the next state and also reward for the action, right? So now in this case, it's a closed loop interaction setting. Like so you take an action, you see how it affects the world, and then you take another action and see how it affects the world. Now, once you have this interactive framework, like so, like the main objective of any reinforcement learning agent is just to maximize the return. Okay. Now, can somebody tell me what is the difference between reward and return?
Reward is like the next reward, the upcoming reward, but return is like the cumulative rewards.
Yeah, so return is just a cumulative reward, right? Like so, like reward is instantaneous, like so next time step you get a reward. But when I say return, it just means that like RT plus 1, the sum of all the future rewards, right? Like so now we also talked about like how to define this efficiently, like so when you have like an infinite episode, right? Like so now in general, like reinforcement learning problems can be classified into like two categories. Like so we have episodic tasks, which means there's a finite termination for the episode like of interaction, and then you get a new episode of interaction, right? Like so in that case, like this reward return that I defined, like which is the sum of the future rewards, is valid mathematically. Like however, there are also a lot of interesting problems which comes under continuing task category. So in the case of continuing tasks, the task just never ends. Okay, it is like one big episode like of infinite steps. Like for example, like a robot which is supposed to clean this campus. Okay, so like it is going to be always cleaning, right? Like so the job never ends. Like it's an example for a continuing problem. Now in the case of continuing tasks, like this sum is going to be an infinite sum, right? Like so now we are kind of trying to maximize something which is infinite, so which doesn't make sense. Like so we need to bound this, like, and this is where we introduced our hyperparameter gamma, right? Like the discount factor. So like when you add gamma, which is usually less than 1, 0, which is between 0 to 1, right? Like so, and discount the future rewards this way, then you have a sum which is not infinite. Okay. Also, the other advantage of gamma is like even us humans, like so we have some discounting. Okay, maybe we don't have the same exponential discounting that reinforcement learning agents use, like, but we do have some discounting, right? Like so, like it is more important that we get, let's say, 100,000 today than $1 million after 10 years, right? Like so, like we value things that are like that comes to us sooner than later. Like so, future is important. Like of course we want to live longer, like, but at the same time, like present is more important, right? Like so, gamma kind of models that. Okay. Now, so this is the setup. Like so, you have an interactive world, and like so, you have different types of tasks that you can do, either episodic or continuing. Now, how do I come up with an agent which would maximize its return? Now, for almost the entirety of this course, like so, we talked about like one mathematical framework to solve reinforcement learning, which is Markov decision process. So in the case of MDPs, like you have a set of states, you have a set of actions, and you have the transition function, which tells you, given the current state and action, which next state would I go to, or the probability distribution over next states. And we also have the reward function, which tells us, given the current state and action, like what would be the reward that I would obtain for this particular action in this particular state, right? Like so now, so you could also add gamma to the definition of MDP, like because by changing gamma, like you have different set of problems to solve. And so this bunch of entities together defines a Markov decision process. Okay. Now, once you have this general mathematical framework, like so now we can talk about like different things. Like so, for example, like how do I learn which state is more useful? Okay. So that is done by learning state value functions. V, right? V functions. So V functions take a state and tell you like how useful is the state. Like so the usefulness of the state is defined as the return that you could achieve by starting from this state, right? Like so, like a state which leads to a better reward will have more value than a state which leads to, let's say, negative reward. So similarly, like we can also talk about how useful is a particular action to take in a particular state, right? Like so that is state action value function. Okay, so state action value function is given by the Q value, Q function, right? Let's say Q of S comma A. Okay, now yeah. Okay, so we can also talk about policy, okay, phi, which takes a state and gives us an action to take from the state, right? Now, we discussed different ways to learn all these entities, right? Like so now our end goal is always to maximize our return, right? Like so now that can be done in broadly two different ways, like as we have seen in the course. Like, so you could take a value-based approach, okay, which means you're learning the value functions, like state value functions or state action value functions, okay, and use this value function to construct the policy, okay, and this policy is going to give you like good, like the best possible return, right? So, and the alternate approach for this is policy gradient methods. Okay. In the case of policy gradient methods, like we completely bypass the value function, estimation of value function, and just say that, can I directly learn a policy, which given the state is going to give me an action, and this policy will aim to get the maximum possible return, right? Like, so now they are both trying to solve the same problem, but in different spaces, okay? So value-based methods solve the problem in value space, like they search over value space. However, like policy-based methods are going to search over the policy space. Even though they are solving the same problem, this kind of like view where like you are searching for the solution in two different spaces, right? Like, so that means that the dynamics of your solutions, like, or the learning process is going to be different. Like, so sometimes you would prefer value-based methods, sometimes you would prefer policy-based methods, right? Like, so typically, like, so whatever we have seen so far, right? Like, so value-based methods are in some sense more sample efficient, like when compared to policy-based methods. Like, so, however, the advantage of policy-based methods is like, if samples is not an issue, then they are really fast learners. Okay, so you could learn easily, like you could learn at scale easily, like if you use some of the policy gradient approaches. Okay, so this is good. Now, the classical method for solving Markov decision process was based on dynamic programming, right? Now, if you remember, like our discussion on dynamic programming, like, so the basic assumption is the transition dynamics of the world is given to you. Okay, so in some sense, you are not learning anything; you are just estimating the policy. Okay, so it's not a learning-based approach. Like in DP, like typically, like you would set up iterative algorithms based on Bellman equations. Okay, so we have seen both policy iteration and value iteration. Which are both trying to estimate the final policy, but based on the transition dynamics, right? Like, so in some sense, there is no learning through interaction in dynamic programming. Like, so in fact, there is no learning there. Like, it is just estimation of policies. Okay, so if you want to talk about learning-based approaches, then we have two classes of learning-based approaches. Like, so, like we have Monte Carlo methods, and we have TD-based methods. Okay. So the basic idea in Monte Carlo methods is like you are doing sample averages. Like, so you do a lot of interactions. Like, so you try to estimate the value functions by using samples. Okay, which is basically an average of the returns that you have seen so far. On the other hand, like TD is kind of a bootstrap approach, right? Like, so, like if you have to distinguish Monte Carlo and TD, so in Monte Carlo, there is no bootstrapping. Like, you have to finish the episode and then compute the average, right? On the other hand, in the case of TD, like you are actually bootstrapping because you are computing an update for the current state's value based on your estimate for the next state's value, right? Like, so you do this one step when you do one step TD, right? Like, so now there are advantages with bootstrapping. Like, so for example, like you don't need to wait till the end of the episode to make your improvements, right? Like, and also sometimes, like for example, let's say you're solving continuing tasks. It is very difficult to use Monte Carlo methods, like because they expect you to end the episode, right? Like, so on the other hand, like you can easily use bootstrapping methods, like so bootstrapping based methods like TD, like so they don't care about whether the task is episodic or continuing, like they're going to learn in every time step. Okay, now which also leads to some issues, like because like you are doing a guess over a guess, right? Like so, which is kind of easy to do in tabular setting, but once you move to function approximation, it's going to be challenging. Okay, so I think roughly, like if I have to summarize all these things, like so, we have seen 3 ways to solve MDP. Okay, so one was DP, then we have Monte Carlo, and then we have TD, and we could also combine these things together, like which is the end step TD. Okay, now in terms of like solving the reinforcement learning problem itself, right? Like so, we can categorize all our discussions as model free oral, like which is what I have described so far, right? And we also have model based oral, which means that you are either having access to the world model or you are learning the world model. Okay, now methods like Monte Carlo, TD, end step TD will fall under the model free category. However, like DP is an example for model based method. But in the case of DP, we are not learning the model. So can somebody tell me a model based method where we are also learning the model? Okay. There is some answer in the chat, but that's not correct. I'm asking for an example model-based algorithm that we have seen. Some of you are going back in your notes if you have notes. Yeah.
Just to make sure that DB is model-based because
Yes, DP is model-based because it has the transition, it has access to the transition dynamics, okay? But it is not a very interesting model-based algorithm because there is no learning in this model-based algorithm. Like model is given, then you're just estimating the policy. So okay, I see a lot of people are scrolling papers, yeah?
Dyna?
Yeah, Dyna. So Dyna framework is an example for a model-based algorithm, like so where you are also learning the model of the world, right? Like so now, well, do we learn the model of the world in Dyna? Oh well, we looked at a very simple tabular case, like but you can extend it. Okay, so but Dyna is just a framework. You can really combine it with any model free algorithm that you want. Like so, I think in the course we saw Dyna Q, which is basically like combining model with Q learning, right? Like so, but you could do Dyna action critique or like Dyna policy gradient, like so whatever you want. Okay, but the basic idea in Dyna is really to learn the transition model. Like so can we learn given the current state and action, like what would be the next state? Also, can we learn like what would be the reward, right? Like so learning the transition function and the reward function, like when combined with any of these model free techniques, like could lead to a model based algorithm. But the other, I think the other algorithm that we have seen is like methods like Monte Carlo tree search, right? Like so, like which is not model based in Dyna sense, like but you have the model of the world and you're using the model to look ahead in the future before taking an action. So this involves planning ahead, right? Like so like you plan what should be the next step by looking at the whole tree of possibilities. Is that clear? Any questions so far? So there was a question in the chat. So what do you mean by sample efficiency? So by sample efficiency, I just mean lesser number of interaction with the world. Okay. Any other questions?
Policy gradient methods also have convergences, more convergences compared to.
Okay, okay, I will come to that. In like that requires us to talk about function approximation. Okay, so I think this. Oh, there is also another main categorization. So I'll just put all these things in one place. I'll try to. So there is also another major categorization, which is on policy. That is off policy. Okay. In the case of on policy methods, there is no difference between current, like the behavior policy and the target policy. But in the case of off policy methods, it is a bit more flexible in the sense you can actually have any like general behavior policy while you can learn about a particular target policy. Okay. Now, couple of questions here. First, can somebody give me an example for on policy algorithm and off policy algorithm? Sarsa is what? On policy. Okay. So an example for off policy? Q learning. Okay. Okay. So yeah, these are good examples like Sarsa for on policy and Q learning for off policy. Okay. The second question. So what is the benefit of going off policy? Okay, I think there are many answers. I think I'll ask all of you. Yeah?
More exploration with the policy.
You can do more exploration. Okay, what about you?
You can still explore.
Sorry, what?
You can still explore a lot while keeping.
Yeah, so you can. Okay, so I think both answers you can explore a lot while safely learning a better policy. Okay, so do you have it?
Yeah, also like say.
Okay, so in general, like you can explore like better and like have like while you are learning the target policy, but there are also other benefits, right? Like so, for example, like if you have a good off policy algorithm, then you can kind of reuse your past experiences. So if you think about why the traditional machine learning, like the supervised learning, is extremely successful right now, it is mainly because of the data. Okay, so of course there are a lot of advances in deep learning, like but all these advances, they are useful because they tell us how to use the data like in a more efficient way, right? Like so in on policy learning, if you're just throwing away all the data, like as and when we see it, like especially when we are doing gradient descent, then we are missing out a lot of things. Right? So we should be able to extract as much knowledge as possible from the data. Now, off policy methods can do that because you can have a replay buffer which has all the past transitions, and which you cannot do with on policy methods, right? Like so with on policy methods, the elements of the buffer will become stale. Like so you cannot use it because it doesn't come from on policy. Like so every time you're making an update to the policy is changing, right? So you cannot do replay buffer with on policy algorithms. However, with off policy algorithms, you can do this replay buffer trick, and hence like be more data efficient. Okay, so this is.
I have a question.
Yeah.
The assignment when we did actor critic methods was still on policy, right?
Yes. So the actor critic methods that you implement in the assignment is still on policy.
So in that we were collecting batches of data and improving the model?
Well, yeah, okay. So it's a spectrum, right? Like, so it was not complete, it was not extreme on policy setting in the sense like you're not learning immediately after the thing, like, but I think it is still on policy because when you are collecting the data, you are not updating the policy. The policy is fixed for, let's say, 50 episodes. You collect the data. Now you can kind of see all these 50 episodes as just one data point, right? So in that sense, it is still on policy. Like, so it will become off policy when you are also updating the data and then reusing. Like you're also updating the policy and then reusing the data. Okay, so there are off policy gradient methods, and there are also like astrocritic style methods with replay buffer, like which are more sample efficient. Okay, so and I think there is also another broad categorization, which is the idea of, in general, like online oral versus offline oral. Okay, a lot of people confuse on policy, off policy with online, offline. Online, okay, this is just, I think, because of the names. So when I say online versus offline oral, so online oral is like all these things that we are seeing here, okay, in this big picture. But offline oral is like what we discussed towards the end of the course, like, so where the idea is you have collected data set of interactions and you are just learning from the data. Okay, so offline oral is in some sense learning without interaction. Okay, but off policy oral is not learning without interaction. Like, you are still learning through interaction. It is just that interacting is by a different policy, and like learning is from experience of the different policies. Okay, so but in offline oral, like, everything is like collected beforehand and you're just learning from the data. Is that clear? Any questions? Okay, so well, I think this gives you, did I miss any of the broad high level categorization? Yeah, I think this is mostly the big picture. Okay, so now this is about how to solve MDP, right? Now, which makes a huge assumption that like you have a lot of other things already taken care of. Okay, so now most of the algorithms that we have seen in the course, like in the beginning, like, so methods like TDE or like Monte Carlo or in-step TD or even simple DynaQ kind of approaches, right? Like, so for most of these approaches, like, so we assumed that the representation was given, like, which was mostly the tabular representation, right? Like, so, and like we did not care too much about whether exploration is going to be hard, right? Like, so in other words, we did not talk much about sparse reward settings. Like, so what happens if reward is extremely sparse? Okay, so in those situations, like any of these classical methods, like, they're going to struggle. Like, all these classical methods, they require some signal to learn. Now, if this signal is very rare, then you cannot learn very easily. Okay, so there are a lot of challenges in solving RL, okay, which is kind of general to all these different techniques. Okay, so well, probably we will take a short break now, given that I don't want to do something in 2 minutes and then continue. So we will take a break now, and we can start at 10:30. So we will talk about higher level challenges at 10:30.